Deep in the icy silence of Chile's Atacama Desert, a telescope scanned the cosmos like a needle searching through the fabric of space-time. Then something strange flickered in the data. A galaxy, but too bright, too old, too massive. It wasn't just unexpected. It was impossible under everything we thought we knew about the expanding universe. What if the cosmos isn't stretching the way we believed? What if the Big Bang didn't echo as we thought? One telescope's glimpse into the ancient night sky may be unraveling a century of cosmic theory. And if it's right, the universe may be far stranger than we imagined. Subscribe if you believe the universe still hides secrets. Join us as we follow the light of a forgotten galaxy and confront a mystery that could rewrite the origin story of everything. In the driest place on Earth, where the sky is so clear it feels like a lens into forever, a silent sentinel stands. The Atacama Desert stretches like a forgotten planet, lifeless, windless, timeless. It's here, under an eternal ocean of stars, that humanity built one of its boldest instruments, the James Webb Space Telescope's watchful cousin, anchored on Earth but peering into ancient light. Nearby, the Alma Observatory listens in millimeter wavelengths, and the European Southern Observatory's VLT scans with optical precision. These aren't just machines. They are our eyes open wide in the dark. In July 2024, a batch of deep field data arrived from the JWS TITS sensors, having stared for weeks into a narrow patch of seemingly empty sky. Scientists sifted through the data like archaeologists, brushing away cosmic dust, expecting faint smudges from ancient starlight. But nestled in the stream of infrared signals was something no one expected. A galaxy too bright, too large, and far, far too old. Its name was quickly designated Galaxy 13. Just another catalogue entry at first, but something felt wrong. According to its redshift, a measure of how much its light has stretched during its journey through expanding space, this galaxy wasn't just old, it was ancient beyond reason. Its light had traveled an estimated 13.5 billion years to reach us, meaning it formed just 300 million years after the Big Bang. But galaxies like this aren't supposed to exist at that time. Not with that mass, not with that structure. It's like finding a fully grown tree inside the seed. NASA astrophysicist Dr. Jane Rigby was among the first to raise an eyebrow. "It's not just early," she said in a press briefing. "It's impossibly early." The consensus forming behind closed doors was unsettling. This wasn't just an anomaly. It was a crack. Viewers, imagine you're an astronomer. You've spent your career mapping the age of the cosmos like rings in a tree trunk. Then suddenly, someone hands you a fossil embedded in rock that shouldn't exist yet. What would you think? Would you doubt the fossil or the calendar? As the data was triple-checked, scientists at ESA and NASA reran their models. The redshift of Galaxy 13 wasn't a fluke. Spectroscopic measurements confirmed it. This wasn't a blurry glitch or a lensing illusion. It was real, and it wasn't alone. Other candidates began to surface. Galaxies like CEE RS 93316, even older, more massive. Structures that shouldn't have had enough time to form under the known rules of galaxy evolution. If these were accurate, then the timeline of the universe, the very sequence we built physics upon, was suddenly out of sync in a hushed lab in Baltimore. At the Space Telescope Science Institute, a team pored over star formation models. The numbers didn't add up. These galaxies didn't just exist early, they appeared mature, with signs of dust, heavy elements, and organized structure. Where had they come from? Outside, the world turned as usual. But in here, under digital starlight, something fundamental had shifted. A theory that stood for nearly a century cosmic expansion and the Big Bang timeline was now in question. The discovery reverberated through global astrophysics communities. In Tokyo, teams began reanalyzing dark matter simulations. In Geneva, whispers surfaced about new inflation models. Some cosmologists were thrilled, others were unnerved. After all, this was the kind of data that doesn't just tweak a theory, it threatens to break it. But the story isn't just about science. It's about us, our place, our assumptions. For decades, the story of the universe was clean. A beginning, a rapid expansion, cooling, structure forming gradually from simple to complex. But now, here was something that defied that narrative. A quiet rebellion from the edge of time. And yet, the galaxy itself was silent. No fanfare, no announcement. Just ancient light arriving on our doorstep, whispering, "You were wrong." What does it feel like to be wrong about the universe? To some, it's exhilarating. To others, it's terrifying. But what if it's neither? What if it's a doorway? Here, in the first chapter of this unraveling, we find not an answer, but an invitation to look again, to ask what else we've assumed is certain, but might not be. To open our minds not only to a stranger cosmos, but a stranger version of ourselves, capable of seeing deeper than ever before. The telescope in the desert had done its job. It had seen further, but what it brought back wasn't clarity. It was a question, and that question would soon ripple through everything we thought we knew about the birth of the universe. At first, GLASSC-13 seemed like a marvel, a rare jewel in the depths of space. But the excitement quickly gave way to something else, confusion, and then fear, because this galaxy was not alone. It was just the first. Weeks after the initial shock, Dr. Erica Nelson, a cosmologist at the University of Colorado Boulder, pulled a late shift in her office. Surrounded by glowing spectrographs and galaxy catalogs spread across her monitor like puzzle pieces from another dimension, she was analyzing a separate field of JWST data from the Cosmic Evolution, Early Release Science Survey, SEERS, and then she saw it, another galaxy, massive, luminous, with a redshift placing it even further back than GLASS-Z13, CEERS-93316. Another outlier. Another ghost. It was like finding a second sunken ship in an ocean where none were supposed to be. Then a third, and a fourth. The data didn't show one anomaly. It revealed a pattern. A quiet, shimmering constellation of impossibilities. Each new discovery tightened the tension. Galaxies that should have taken billions of years to evolve were apparently thriving just a few 100 million years after the Big Bang. But how? Under current models of cosmic evolution, this kind of structure formation requires time, a lot of it. Dark matter, halos, need to coalesce. Hydrogen must collapse into stars. Supernova must seed the cosmos with heavier elements. All of this takes time, and yet these galaxies seemed to have skipped the line. Nelson called her colleague, Dr. Ivo Lab in Australia, mid-morning his time. "They're not flukes," she said flatly. "There are more of them." Lab went quiet for several seconds. Then he replied, "We're either looking at the earliest, fastest builders in the cosmos, or we're looking at something wrong with our entire framework. What if these galaxies weren't exceptional? What if they were typical, and we had simply never seen them before? If that's the case, then our entire understanding of the early universe is based on an incomplete, distorted sample. For decades, we were blind to this light, not because it wasn't there, but because we didn't have the eyes to see it. JWST changed that. Its unprecedented infrared sensitivity allowed it to cut through the cosmic veil, revealing galaxies whose light had been redshifted beyond the reach of previous telescopes like Hubble. But in doing so, it may have lifted a curtain we weren't ready to look behind. One by one, the galaxies emerged. Spectral fingerprints confirmed their distance, and they weren't faint shadows. They were luminous, star-forming beasts, burning bright in what should have been cosmic infancy. Were these the cosmic equivalent of ghosts, remnants of some forgotten physics? Dr. Nelson began calling them ghost galaxies, not because they were dead, but because they haunted the timeline of the universe itself. And this raised a deeply uncomfortable question. If these galaxies are real, are we wrong about the age of the universe? Or are we wrong about how galaxies evolve? Viewers, pause here and imagine. You've been taught the universe is a gradually unfolding story. But now, imagine finding the final chapters written on page 1. Would you throw out the book, or rewrite the rules? Meanwhile, a flurry of papers began circulating in preprint servers. Massive galaxies at high redshift, early star formation in the first 300 mir, challenging the standard model with JWST. Theoretical physicists scrambled to modify structure formation algorithms. Could exotic dark matter models explain this, or faster than expected cooling processes? Others weren't so convinced. Some skeptics argued these galaxies might be gravitationally lensed, distorted and magnified by intervening matter. But follow-up studies showed that for most of them, lensing could not explain their apparent brightness or structure. Then came the deeper horror. When compared across multiple filters, these galaxies showed signs of evolved stellar populations, meaning some of their stars had already aged, died, and contributed material back into the interstellar medium. These weren't just early galaxies, they were ancient ecosystems, and if that's true, how many generations of stars had already come and gone before Galaxy 1-3 even emitted its first light? The timeline was fraying. The standard model, Lambda CDM, had long served as our cosmic compass. But now that compass was spinning. What direction was early? What was late? What if time itself, as we understand it, wasn't flowing as smoothly as we thought? Amid all this, the human element was often forgotten. But in interviews, you could hear it, the weight in the voices of the researchers, a quiet awe, a hint of nervousness. Like spelunkers who had stumbled into a cavern that went much deeper than anyone expected. We may be looking at a deeper order, Dr. Nelson said in one interview. Or we may be looking at chaos. So we ask again, are these galaxies rare miracles? Or did we simply misunderstand what the early universe looked like? The ghosts of galaxies past are speaking, and they are rewriting the first pages of cosmic history. Would you like to continue to the next chapter? You said. Continue. To next chapter. Strictly follow word count. In the 1920s, Edwin Hubble looked out into the cosmos and noticed something astonishing. The light from distant galaxies wasn't just faint, it was stretched, shifted toward the red end of the spectrum, like a siren dropping in pitch as it moves away. This phenomenon, known as redshift, became the cornerstone of modern cosmology. The farther away a galaxy is, the redder its light becomes, and thus, the faster it must be receding, Due to the expansion of space itself, redshift was elegant, predictable. It gave us a ruler to measure the depths of the cosmos, a simple equation. More redshift, more distance. More distance, more time into the past. But what if that equation no longer works? In 2024, as more JWST data poured in, that very question began to surface in murmurs. Then in headlines, Dr. Raj Patel, a theoretical physicist at Caltech, had spent his career refining the math behind redshift-derived distances. For him, redshift was gospel. But when he compared the new galactic distances derived from JWST with their apparent mass and maturity, something broke. The numbers didn't just strain the model, they shattered it. How can a galaxy 13.4 billion light-years away already contain stars that are over 500 million years old? He asked aloud during a team Zoom call. It's like finding an adult in the delivery room. The tension was palpable, because redshift wasn't just a measurement tool. It was the backbone of our cosmic story, the very method by which we plotted the timeline of the universe. If redshift lied, then every date we'd assigned to every event in the cosmos, from star birth to galaxy collisions, could be wrong, and yet the data didn't lie. These galaxies weren't just red. They were redshifted so far that they bordered on the opaque curtain of the cosmic microwave background, the very edge of observable time. According to redshift, they existed barely 300 million years after the Big Bang, and yet they looked old. So Patel did what any physicist must do when faced with an impossible result. He questioned the tool. He ran simulations. Could gravitational lensing make a younger, closer galaxy appear redder and older? Possibly, but most of the candidate galaxies didn't show lensing arcs or foreground masses. Could dust redden the light like cosmic smoke in the air? Some, but not all. Then he considered something more unsettling. What if the universe's expansion wasn't behaving the way we thought? The standard model assumes space stretches uniformly. That's what causes redshift. The wavelength of light is literally dragged out by expanding space. But what if that expansion varied in the early universe? What if it accelerated earlier than expected, or was patchy, uneven, turbulent? The implications were enormous, because then redshift wouldn't be a universal ruler, it would be a local, distorted one. And if that's true, how many of our past measurements are miscalculated? Let's put it into metaphor. Imagine you're measuring the distance to a mountain by the pitch of its echo. But now you find out the air between you and the mountain is rippling, warping, stretching, sometimes fast, sometimes slow. How accurate is your echo now? This was redshift's last stand, and some researchers were beginning to suggest that the problem might not be in the galaxies, but in the redshift distance relationship itself. An international team from Heidelberg proposed a variation of tired light theory, an old idea that suggests light loses energy simply by traveling through space, not because of expansion, but because of interactions with unknown cosmic particles. Though widely dismissed in the past, the team now suggested JWST's observations may demand a modern revisit. Of course, these suggestions stirred controversy. The idea that redshift wasn't purely from expansion threatened to dismantle decades of established cosmology. It reeked of scientific heresy. And yet, the galaxies persisted. Each new observation from JWST further challenged the standard interpretation. Galaxies with surprisingly high metallicity, star formation rates that should take billions of years, happening in a few hundred million. The redshift math said one thing, but the galactic archaeology said another. Patel summarized the crisis in a single sentence during a press Q&A. Either the galaxies are lying, or the universe is. So, what's more likely? Some scientists proposed hybrid models. Perhaps expansion occurred alongside unknown interactions. Or perhaps early dark energy skewed early redshift readings. Others doubled down on the existing model, urging caution. Maybe JWST's sample was biased. Maybe calibration errors crept in. Maybe we simply didn't understand early galactic evolution as well as we thought. But even the skeptics were rattled. Because if redshift could no longer be trusted, the implications would reach far beyond astronomy. Cosmology, particle physics, even the origin of time itself, all rely on that stretched light as evidence. So we return to a familiar question. What if everything we knew was wrong? As you're watching this, ask yourself, if our cosmic ruler is broken, how do we measure truth in the universe? Redshift once mapped the stars. Now it may be just another myth, a beautiful illusion born from the limits of our understanding, and beyond that illusion, something deeper may be waiting. We were raised on a singular idea, that the universe began with a bang, a moment of everything from nothing, a rapid expansion, then cooling, stars, galaxies, us. The Big Bang wasn't just a scientific theory, it became our cosmic genesis, our shared origin myth, dressed in equations and background radiation. But what if that story is incomplete? What if the universe didn't begin, but began again? In the wake of the impossible galaxies discovered by JWST, questions began to circulate in corners of the scientific community that were once considered fringe. The standard cosmological model was under pressure. The timeline wasn't adding up, and cracks like these tend to let in strange light. One such beam came from the mind of Sir Roger Penrose, the Nobel Prize-winning physicist had long proposed an alternative view of cosmic history, the conformal cyclic universe. In Penrose's model, the universe doesn't begin and end, it repeats, over and over. Each eon, as he calls it, ends in the death of all mass and the beginning of a new cycle. To us, it would look like a big bang, but it would actually be the aftermath of a previous universe, gently fading into ours, when JWST began showing galaxies that were already mature just 300 million years after the supposed birth of time. Penrose's ideas returned from the theoretical shadows. Was it possible that we were seeing not the first galaxies, but the last embers of a previous cosmos? Penrose wasn't alone. Loop quantum cosmology, a field emerging from attempts to merge general relativity and quantum mechanics, suggested that the Big Bang might actually be a big bounce. In this theory, the universe contracts before expanding, avoiding a singularity. Altogether, our current expansion is just the latest in a series of bounces, like the heartbeat of a breathing cosmos. If these ideas seem speculative, even mystical, consider this. Every major challenge to a dominant theory once began as heresy. Quantum mechanics was unthinkable, relativity absurd, the heliocentric model blasphemy. And now, with JWST peering further than ever before, we might be catching the fingerprints of something bigger than a single expansion. Dr. Marina Cortes, a theoretical physicist in Edinburgh, studies time asymmetry, the one-way direction of time. She suggests the earliest structures we're seeing may hold entropic signatures from a previous cycle. In plain terms, leftovers, like seeing ashes in a fireplace and wondering who lit the fire before you arrived. But how would we prove it? Some believe the answers could lie in the cosmic microwave background, the faint afterglow of the Big Bang. Penrose himself, along with Vahey Ghazardian, once claimed to find Hawking points in the CMB circular patterns that they argued could be remnants of black holes evaporating in a previous universe. The scientific community remains divided. Some call it noise, others call it a message. JWST, however, doesn't study the CMB. It looks deeper into infrared, capturing light from stars and galaxies. But that light, ancient redshifted bent, might still carry signatures of a prior eon, and it might be whispering that the universe we live in wasn't born but inherited. Imagine for a moment a galaxy that appears impossibly old, not because it's the product of rapid evolution, but because it was born old, carried over, a cosmic artifact from before the last reset. And if time itself is cyclical, then what does that mean for us? Are we destined to repeat? Are we echoes of civilizations past? Could life, too, be a recurring pattern, an inevitable emergence in each cycle? Philosophers and physicists alike have long pondered this. Eternal return, the wheel of time. Ancient beliefs mirrored in modern math. Of course, many mainstream scientists urge caution. Extraordinary claims require extraordinary evidence. The JWST data may still yield more conventional explanations, revised models of galaxy formation, unknown mechanisms of dust production, or simply rare, extreme environments in the early cosmos. But even those voices admit the evidence is mounting, and with each new image, the Big Bang feels less singular. Viewers, picture this: you're standing on a shoreline, watching waves crash one after another. If all you'd ever seen was the latest wave, you might believe the ocean began with it. But now, imagine stepping back and realizing the waves never stopped. If the universe is a cycle, not a straight line, then the Big Bang wasn't a beginning. It was just the crest of the latest cosmic wave. And what JWST has found may be the first evidence that there were waves before us, and there will be waves after, a bang or a breath, a singularity or a rhythm. Whatever the answer, it changes how we see everything, from time to origin to fate. Because if the universe didn't begin once, then maybe neither did we. Time, we believe, flows like a river, forward, predictable, unstoppable. We measure it in seconds, in years, in light, in distance. The farther something is, in space, the older it must be. That's the logic. That's the foundation. But what if time isn't what it appears to be? What if our most sacred tool for reading the cosmos, the very timeline of the universe, is nothing more than a mirage? In late 2024, a group of researchers from the University of Tokyo, led by Dr. Kenji Nakamura, proposed a startling idea that the ancient galaxies discovered by JWST may not be as far or as old as we think. Their theory didn't deny redshift, it reimagined it. Nakamura called it chronospatial refraction, a hypothetical phenomenon in which light passing through warped regions of space-time could be redshifted not by expansion alone, but by gravitational interference on an intergalactic scale. In other words, the light we see might have been bent through time, not just space. This would mean our cosmic distance ladder, built so confidently on redshift measurements, is warped. We could be looking at nearby galaxies masquerading as ancient ones, or worse, ancient galaxies displaced into false coordinates by the warping of spacetime itself. It's a radical notion, but it's not without precedent. Einstein's theory of general relativity showed that gravity warps not just space, but time. Time moves slower near massive objects, a fact proven by satellites in orbit, and clocks placed on mountains, ticking slightly faster than those at sea level. If gravity can stretch and compress time locally, what happens when light journeys across billions of light years through the deep wells of unseen mass and dark energy? Nakamura's team built simulations, virtual universes, seeded with massive clumps of dark matter and hidden topological defects known as cosmic strings. These exotic relics, predicted by some inflationary models, could act like invisible gravitational lenses, not just bending light, but scrambling its TIM-ESTAMP. When they ran JWST's galaxy data through this simulated map, something eerie happened. Several ancient galaxies snapped into younger positions. The redshift remained high, but the actual travel time, once distortion was accounted for, was shorter, like a voice echoing in a canyon. The signal hadn't traveled as far as we thought, just through more obstacles. If true, this could explain the seemingly impossible maturity of the early galaxies. They didn't evolve faster. We just misread their arrival time. But this, too, presents a problem, because if light can be warped through both space and time on intergalactic scales, how do we ever know how old anything truly is? Imagine watching an old film reel with warped, melted edges. The frames are jumbled, the order is off, the ending plays before the beginning. That's what Nakamura says. Our view of the cosmos might be not a clear history, but a distorted playback, and the implications don't stop at astronomy.cosmic time. Our idea of before and after in the universe underpins all of physics. From entropy to causality, everything we know relies on time behaving in a linear, measurable fashion. But if deep space warps not just where light goes, but when it appears to come from, then the early universe may not be early at all. Dr. Lisa Randall at Harvard, a prominent theoretical physicist not involved in the study, responded cautiously but curiously. It's a reminder that in cosmology, perception is shaped by distance, and distance is shaped by assumptions, she said. It's possible our entire concept of cosmic time is filtered through a lens we don't fully understand. This raises a haunting question. Are we staring at the past? Or are we trapped in a funhouse mirror, seeing reflections that don't belong to any real moment? JWST, for all its power, still relies on light, and light, for all its consistency, still follows the shape of the universe. If that shape is twisted, then so is our truth. Viewers, consider this. What if you woke up one day and realized your memories weren't chronological? That your past, your future, your now, all happened out of order? How would you know what was real? How would you define reality? This is the position modern cosmology now faces. If time is malleable on large scales, then maybe the universe didn't evolve smoothly at all. Maybe it's always been more chaotic. A tangle of events, a storm, not a river. Of course, many physicists still hold firm to the standard model. The distortions proposed by Nakamura's team are unproven. We have no direct evidence of cosmic strings or extreme temporal lensing. And yet, the anomalies persist. Galaxies that shouldn't be there, structures that shouldn't yet exist, time that doesn't behave. And so we are left with two choices: believe the timeline or question the frame through which we see it, because when light bends, so does truth. In the grand architecture of the cosmos, expansion was the constant. Ever since Edwin Hubble discovered that galaxies were moving away from us, the farther, the faster, we believed space itself was stretching like dots on an inflating balloon. It gave us a tool, the Hubble constant, a single number that told us how fast the universe was expanding. A cosmic speedometer, but in recent years, that number has started to fracture. Two different methods of measuring the Hubble constant have produced conflicting results. One, using the local universe, supernova, Cepheid variables, nearby galaxies. The other, using ancient echoes, the cosmic microwave background, observed by the Planck satellite. The discrepancy was small at first, then it grew. And now, with the James Webb Space Telescope casting its gaze into the deep past, that crack is becoming a canyon. They call it the Hubble tension, and it may be the first domino to fall in the collapse of our standard model in 2024. Nobel laureate Dr. Adam Rees, one of the key figures behind the accelerating universe discovery, publicly stated, "This is no longer a measurement error. This is a signal." His team, using JWST's precision, remeasured distances to local Cepheids with unparalleled clarity. The result? The tension didn't shrink. It sharpened. Rees's measurements showed an expansion rate of 73.0 kilometers per second per megaparsec. Planck's cosmic background data pointed to 67.4. The error bars no longer overlapped. That's a 5+ sigma discrepancy, a level at which physicists typically accept a new discovery. But what exactly is the discovery, and what does it mean? The leading theory suggests something profound. Our cosmological model, lambda CD, may be incomplete. Lambda CDM includes dark energy lambda, cold dark matter CDM, and assumes a flat, expanding universe governed by general relativity. It has been our best fit model for 2 decades. But now, it no longer fits. Some suggest early dark energy, a brief, high-powered push of expansion shortly after the Big Bang, could explain the discrepancy. Others point to phantom energy, a hypothetical force that grows stronger over time, accelerating expansion in strange and unpredictable ways. Still others suggest a breakdown in the assumption of homogeneity, that maybe the universe isn't the same everywhere, and our local measurements are being skewed by a cosmic bubble or void. But here's where things become even more unsettling. JW, originally designed to explore the early universe, began offering clues that the expansion rate might not just differ over time, but across space. Dr. Janina Linhart, working with the European Space Agency, found that galaxy clusters observed in opposite hemispheres of the sky showed slightly different rates of separation. It was subtle, fractions of a percent, but persistent. Could this mean the universe isn't expanding uniformly? If so, the implications are staggering. It would mean that the very fabric of space behaves differently depending on where you look, undermining one of the most sacred assumptions in cosmology, esotropy, that the universe looks the same in all directions. Some dismissed it as statistical noise. Others saw a whisper of new physics. Dr. Rees remained cautious but open. JWST is doing more than confirming anomalies, he said in an interview. It's forcing us to rethink the scaffolding of the cosmos. And this raises a haunting question. What if we've mistaken simplicity for truth? For decades, cosmology has preferred the elegant models that are clean, minimal, explain everything in a handful of parameters. Lambda CDM was beloved, not just because it worked, but because it felt right. But now, the universe is reminding us, reality isn't obligated to be elegant viewers. Take a moment and consider this. If the rules of the cosmos changed over time, or shifted across space, would we even notice? Or would we keep forcing a single equation to fit a universe that refuses to be boxed? This is the essence of the new Hubble. Tension, it's not just about two conflicting numbers. It's about what we believe the universe is: a uniform, predictable machine, or a dynamic, evolving mystery. More radical theories have begun to surface, including modifications to general relativity, interactions between dark matter and dark energy, and even suggestions that the speed of light itself may have changed. Over time, each of these would represent a seismic shift, the kind of theory that rewrites textbooks, and yet the scientific community is split. Some argue for caution, urging patience as more data arrives. Others say the time for patience has passed, that the evidence already demands a new paradigm. Meanwhile, JWST continues its mission, one deep field image at a time. Its infrared eyes peeling back the layers of cosmic time, and with each new glimpse, the tension grows, not just in numbers, but in us, because deep down, we want the universe to make sense. We want our models to hold. We want certainty. But perhaps certainty was never part of the design. In the world of science, data is sacred, but only when it obeys. When it doesn't, it becomes a problem, a silent rebellion, an anomaly. And anomalies have a way of testing our convictions. By late 2024, the headlines were growing louder. JWST galaxies break the universe. Cosmic history in crisis. Redshift reconsidered. But beneath the sensationalism, serious questions pulsed like gravitational waves through the heart of cosmology. Were we truly seeing something new, or just misreading the stars? That's where skeptics entered the story. Scientists, not driven by stubbornness, but by caution. Among them was Dr. Rachel Livermore, an astrophysicist at the University of Texas at Austin. A respected researcher with years of experience analyzing higher redshift galaxies. Livermore wasn't ready to throw out the standard model just yet. She gathered a small team to reprocess JWST data independently, rechecking calibrations, re-evaluating redshifts, and reconsidering how starlight behaves at the farthest edges of the observable universe. If the data's wrong, she said during a symposium, we have to know. But if the data's right, then we're standing on a cliff. The team began with the basics. Spectral analysis. Every galaxy's light is a fingerprint, lines and dips, revealing its elemental makeup and velocity. By measuring how far these lines are shifted toward red, astronomers determine how fast a galaxy is receding, and by inference, how far away and how far back in time it lies. But what if those fingerprints were smudged? Livermore's team re-examined a sample of ultra-higher redshift galaxies, including Glassy 13, CEERS 93316, and others that had raised eyebrows around the world. They questioned everything. Could interstellar dust be mimicking redshift? Could the instruments themselves introduce distortion? Could foreground objects be contaminating the signal? The answer was no. Or at least, not enough, the redshifts held. Spectroscopic confirmation supported the distances, and the galaxies still looked too old, too structured, too luminous for their place in time. Then came the hypothesis of gravitational lensing, that massive objects in the foreground could bend light from distant galaxies, magnifying and brightening them, making them appear closer and more mature than they really are. It was a reasonable objection. Lens-induced illusions are well documented in cosmic observations, so the team cross-referenced the JWST fields with gravitational lensing maps from Hubble and ground-based observatories. A few of the galaxies were slightly lensed, but most had no foreground lenses strong enough to explain the anomalies. The light was real, and so, it seemed, was the problem. By now, the discussion wasn't just scientific, it was philosophical. How do we react when reality contradicts our models? Livermore herself acknowledged the unease. There's a point, she said, where trying to preserve the model becomes more absurd than updating it. Still, she pushed further. Maybe the redshift measurements were being interpreted through flawed assumptions. Could unknown dust compositions alter infrared readings? Could early galaxies be more efficient at star formation than we thought? The answers were tentative, but consistent. Some adjustments could account for parts of the puzzle, but not the whole. The galaxies remained impossible. At an international conference in Copenhagen, Livermore presented her findings with sober clarity. We've tried to break the data, she said. It won't break, it keeps pushing back. And here lies the essence of Chapter 8. Because when data fights back, you face a choice. Fight harder to protect your belief system, or listen to the whisper in the numbers. The scientific method, at its best, welcomes contradiction. It doesn't treat anomalies as threats, but as invitations. And yet, there's a human element we can't ignore. Careers built on theories, reputations tied to equations. Paradigm shifts are not just intellectual, they're emotional. Viewers, imagine devoting your life to a model of reality, only to have it questioned by a few pixels of distant starlight. Would you resist, or would you adapt? The JWST findings didn't just challenge our view of the early universe. They revealed something deeper, a resistance within the scientific community itself, not from arrogance, but from fear. Fear of uncertainty. Fear of losing the map we've used to navigate the infinite. But this is where science differs from dogma. It allows correction, it demands it, and as more research teams from Heidelberg, Tokyo, Cape Town, and São Paulo joined the effort, the picture became clearer. The galaxies were real, the data was good, and the story we'd been telling was missing pages. Livermore concluded her report with a single, resonant line. If the model breaks, let it break, and let something more beautiful emerge in its place. Because sometimes, to move forward in science, we must first allow our certainty to collapse, and from the wreckage, listen to what the data is trying to say. By late 2024, a quiet chorus had begun to rise across observatories worldwide, not in words, but in signals, faint patterns in the sky, shapes that repeated where randomness was expected, galaxies behaving like synchronized dancers in a choreography no one had taught them. From South Africa's remote Karoo Desert to the forests of Guizhou in southern China, telescopes tuned to different wavelengths were hearing the same strange rhythm. These were echoes of the impossible. It began at Meerkat, an array of 64 radio dishes stretching across the South African landscape. While surveying neutral hydrogen emissions from deep space galaxies, astronomers detected unexpected clustering patterns. Galaxies appeared to be aligning too coherently. Their angular momentum vectors, their spins, seemed correlated across vast cosmic distances, far beyond what standard cosmology predicted. Independently, FATH, the 500-meter aperture spherical telescope in China, was conducting a sky survey in a different band. It too noticed anomalies, discrete galaxy groups, billions of light years apart, appeared to oscillate in brightness in similar cycles. The correlation was weak, but statistically significant. Could these be artifacts? Data processing glitches? Both teams reanalyzed. They scrubbed their pipelines, ran artificial noise tests, added independent cross-checks. The patterns remained, and, slowly, a picture began to form. Somewhere in the depths of space, there seemed to be a structure, not physical, not visible, but mathematical. A kind of rhythm, a frequency imprinted into the large-scale distribution of galaxies. This wasn't just clustering, it was choreography. At the University of Toronto, astrophysicist Dr. Eleni Markosian took the lead on analyzing these emerging alignments. She compared Myakati's spin alignment data with JWST's deep field images and made a discovery that sent shivers through the research team. Some of the same regions where ancient massive galaxies had emerged also showed signs of spin coherence, galaxies rotating in harmony, as if responding to a shared instruction. This is either a coincidence of the highest order, Markosian wrote in her first draft paper, or the fingerprints of a deeper order beneath the observable universe. The term caught on, hidden architecture. What could cause it? The Standard Model predicts that early galaxy formation was chaotic, driven by quantum fluctuations, stretched out by inflation. Over time, gravity built structure, but it was noisy, messy. The idea that galaxies could form with synchronized properties across billions of light years bordered on heresy, unless something was guiding it. Markosian proposed a new idea, primordial patterning, an unknown field perhaps related to dark energy or early universe physics that seeded not just density fluctuations, but spatial alignment. Others went further. Theorist Dr. Leo Wang at Seoul National University speculated that these echoes could be signatures of a pre-existing cosmic topology, a non-Euclidean structure the universe inherited from whatever came before the Big Bang. If space itself has shaped loops, folds, resonant cavities, then waves of matter might naturally fall into synchronized modes. Think of a drum. Strike it anywhere, and vibrations ripple out. But those ripples follow the shape of the drumhead. They resonate in patterns defined not by the strike, but by the geometry. Is our universe ringing? And are these ancient galaxies simply tracing the contours of that vibration? JWST's infrared eyes can't see these structures directly, but it can see their effects. Galaxies where they shouldn't be, aligned when they shouldn't align, glowing in frequencies that suggest more than randomness. The echoes grow louder. Viewers, close your eyes and imagine the universe not as a void, but as a vast cathedral. In it, every particle hums, every photon sings, and what we're beginning to detect are the harmonics of creation. Of course, the establishment pushed back. Critics pointed to selection bias, too statistical, cherry, but each new observatory added fuel. LOFA, air in the Netherlands, SKA, precursors in Australia. Even historical data sets from Sloan Digital Sky Survey began to show hints, once filtered with new algorithms. If this hidden architecture exists, what does it mean? Perhaps it suggests that space isn't as empty as we thought, that beneath galaxies and stars, beneath dark matter and even quantum fields, lies a scaffolding, a cosmic lattice that shapes how everything moves. A force, a memory, a leftover from before time began, or something else. Dr. Markosian, during a conference in Prague, leaned into the question. Maybe we've been studying the dots, she said, but never asked who drew the lines between them. The idea is as humbling as it is terrifying, that the universe may not be a canvas of randomness, but a symphony, and if it is, someone or something composed it, and so the whispers continue through galaxies that rotate in unison, through light that pulses with an ancient beat, through formations that defy chaos. The echoes are not noise, they are signals. The question is, are we ready to listen? For decades, it's been the invisible scaffolding holding our universe together. Dark matter, we can't see it, we can't touch it, but without it, nothing makes sense. Galaxies spin too fast, clusters defy gravity, light bends in ways it shouldn't. Dark matter, the quiet titan, was supposed to be the glue, the silent architect, but now it might be betraying us. As JWST peers deeper into cosmic history, it continues to uncover galaxies forming earlier, faster, and more massively than ever predicted. These galaxies are not only old, they're organized. Spiral arms, bulging centers, structured formations that should require billions of years, and vast halos of dark matter to stabilize and support them. But where is the evidence of that scaffolding? In simulations, dark matter halos provide the gravitational framework upon which galaxies form. They gather clouds of hydrogen, shape star formation, and ensure galaxies don't fly apart from their own rotation. But JWST's early galaxies, some just 300 million years post-Big Bang, seem to be thriving without any visible dark matter support. Their light curves, their density, their organization, all suggest mass and structure, without the mass to explain it. At CERN, particle physicists like Dr. Leon Marching were baffled. If these galaxies are what they appear to be, he said in an interview, then either dark matter behaves very differently in the early universe, or we've misunderstood it entirely. It wasn't the first time dark matter had slipped through our fingers. For over 50 years, we've hunted for it. Detectors buried beneath mountains, colliders pushing atoms to their limits. Yet nothing definitive, no direct detection, no particle, no interaction we can measure. And now, in the crucible of cosmic infancy, the absence grows louder. At Fermilab, simulations ran day and night. Teams input JWST's newly observed galactic masses and spin rates. The computer models, based on lambda CDM, struggled. Galaxies collapsed too late, spun too fast, dispersed too quickly unless massive halos of dark matter were present. But JWST wasn't seeing the gravitational effects expected of such halos. No strong lensing, no extended mass profiles. The early galaxies behaved as though they were built from visible matter alone. Baryons, stars, dust, and little else. Could dark matter be more ephemeral in the early universe? A fluid state, a weaker interaction, or was it never there to begin with? Some theorists began revisiting modified Newtonian dynamics, MOND, a fringe idea once dismissed. It suggests gravity behaves differently at very low like those in galactic outskirts. MOND had trouble fitting the full range of cosmic observations, but suddenly it didn't seem as absurd. Perhaps the laws we use to interpret gravity break down under certain conditions, especially in the first few 100 million years after the Big Bang. Others proposed exotic ideas that dark matter decays or transforms over time, that it didn't exist yet in those early galaxies, or that it exists in another dimension, a hidden brain seeding gravity across membranes of reality we cannot yet perceive. It sounds like science fiction. But when the data doesn't match the model, fiction becomes possibility. Viewers imagine building a skyscraper, expecting steel girders inside. But when you tear open the walls, it's standing unsupported. How do you explain it? Dr. Zara Khan, working with the Euclid mission team, called it a betrayal of expectations. In her analysis of early universe galactic dynamics, she found the structures were too coherent, too strong, too early. She paused during her TEDx talk and said, "Either something else is holding these galaxies together, or they were never unstable to begin with. But how can that be? Is there an undiscovered force operating only at high redshifts? Are we misinterpreting rotation curves due to relativistic distortions? Or is the cosmos asking us to let go of our deepest, most persistent assumption? Dark matter was never directly seen, only inferred. A ghost in the equations. A necessary patch. And now, with the early universe refusing to obey the laws we wrote for it, that patch is coming loose. And yet, the betrayal is not violent. It's silent, unfolding in silence, in the vacuum of deep time, in galaxies that burn without the fuel we expected. One image, in particular, stood out. JWST captured a compact, ancient galaxy, labeled JADE-C SC120, with over 1 billion solar masses, packed into a small radius. Its rotation was stable, its light smooth, but its halo. Missing it is, quite possibly, the first confirmed galaxy without enough dark matter to explain its form. And it's not alone. This raises the deepest question. Yet, what if dark matter isn't fundamental? What if it's a symptom, a placeholder, for a deeper reality we have yet to understand? Not just invisible matter, but a signpost pointing toward new physics, something older, something stranger, something foundational, because when the silent scaffolding collapses, what's left isn't chaos, it's revelation. At first, they were called anomalies, then chronological outliers. Now, they have a name that sends chills down the spines of cosmologists around the world: the forbidden galaxies. Galaxies that shouldn't exist, by any known rule. Galaxies that break the cosmic script. Massive, structured, chemically mature, and somehow ancient beyond reason. If the universe is a timeline, these galaxies are out of place. Too early, too advanced. Too complete. It's not just one or two. It's not a glitch. Across multiple deep fields observed by the James Webb Space Telescope, researchers have now catalogued dozens of galaxies that defy cosmological models. They lie at redshifts greater than 10, some even 13. That places them just a few hundred million years after the Big Bang, a time when the universe should have been dark, chaotic, and still assembling its first stars. And yet, here they are. Among them is CEERS 1749, an extraordinary case discovered during the Cosmic Evolution Early Release Science Survey. It exhibits a mass comparable to the Milky Way, but exists just 500 million years after the beginning of time, with clear signs of heavy element enrichment. In theory, such a galaxy would require more time than had even passed by that point in the universe's life. It's as if you found a fully constructed cathedral, stained glass, arches and all, in the ashes of the first campfire. So how do we explain them? Some researchers say we can't. In a recent paper from MIT, Dr. Sarah Wogelsberger called these systems chronologically forbidden, invoking the phrase used in geology for fossils found in impossibly old strata. The universe, she wrote, appears to have skipped a step, or maybe several. Others offer gentler explanations. Perhaps these galaxies formed in rare pockets of ultra-dense matter, allowing for accelerated evolution. Perhaps star formation in the early universe was hyperefficient, forming not in slow trickles, but in sudden, violent bursts. But even these attempts strain under the weight of the data. What would normally take billions of years seems to have happened in just a few 100 million. And it's not just the age, it's the structure. Some forbidden galaxies show signs of disk formation. Others appear quenched, meaning they've already stopped forming new stars. Some even suggest early galactic mergers, a process that requires complexity, gravity wells, and long periods of interaction. How did galaxies this mature emerge so early in what was supposed to be a chaotic, primal time? If these galaxies had appeared in simulations even 5 years ago, they would have been dismissed as programmatic errors, as bugs. Now they're real, measured, spectroscopically confirmed, and they're everywhere. On citizen science platforms like Zooniverse, amateur astronomers comb through JWST imagery. More than once, volunteers have flagged objects that later turned out to be forbidden galaxies. One user, going by the handle Quiet Quark, commented, "I didn't know what I was looking at. It just didn't seem to belong." And maybe that's the point. These galaxies don't belong. Not in our models, not in our understanding. They exist at the intersection of science and myth, where certainty fades and the cosmos begins to whisper its secrets again. Dr. Marcela Reyes, a theoretical physicist at Caltech, addressed the tension in a now viral keynote. "We thought we had a narrative," she said. "Big Bang, inflation, structure formation. But these galaxies are like pages from another book, one we haven't read yet." She paused, "Or maybe one we've forgotten." The phrase caught on. Forgotten galaxies. It evokes something beyond physics, a sense that we're rediscovering a version of the universe we once knew but lost. As if the cosmos, in revealing these ancient titans, is reminding us that its story is more complicated, more mysterious, and far less linear than we assumed. But perhaps the most chilling possibility is also the simplest. Maybe the forbidden galaxies were always there. Maybe we just lacked the tools to see them. JWST didn't rewrite the universe. It revealed it. Viewers imagine walking through a museum of ancient artifacts. You're told these relics belong to a certain era. But then, in the shadows, you find objects too advanced, too refined, to fit that story. What do? Do you hide them, ignore them, or do you rewrite history? The forbidden galaxies aren't just astrophysical puzzles. They are philosophical provocations. They challenge our desire for order, our assumptions about causality, and our very sense of time, because if galaxies can grow faster than time allows, then what else can break the rules? What else have we misread in the cosmic script? The sky is no longer a window. It's a mirror, and in it we're seeing reflections that don't belong to the present or the past. They belong to something else, something outside. In science, revolutions don't always arrive with thunder. Sometimes they come in whispers, a sentence removed from a textbook, a footnote added in the margin, a lecture slide quietly revised before class, and sometimes, when the data hits too hard, the change begins not with headlines, but with silence. By the end of 2024, the shock of the James Webb discoveries had begun to wear off, but in its place grew something deeper: unease. In universities around the world, cosmology professors found themselves hesitating, pausing before answering student questions, rethinking how to explain a universe that no longer obeyed the rules they had devoted their lives to teaching. There was no official declaration, no formal retraction of the standard model, but you could feel it. A soft rewrite was underway. It started with conference presentations. Slides that once used Hubble timelines now had asterisks. Models that once ended confidently at 13.8 billion years now carried ellipses. Phrases like unexpected formation and challenges to theory began appearing in the abstracts of major journals, carefully worded, strategically cautious. The foundation hadn't crumbled, but cracks were showing, and the people who built that foundation were quietly patching. At Princeton, a revised syllabus for Cosmology 301 removed an entire week on epochs of early galaxy formation and replaced it with a section called Current Anomalies and Open Questions. No dramatic announcement, just an edit. A subtle acknowledgement that what was once solid had become speculative. At Cambridge, a lecturer rewrote the opening line of their Big Bang module from "The universe began 13.8 billion years ago" to "according to our current best model." It was a small shift, but words matter. In private, the conversations were more honest. In hushed faculty lounges, in email threads between collaborators, the tone was changing. One physicist admitted, "In confidence, we're in a holding pattern. The model doesn't fit anymore." But no one wants to say it out loud, because to say it out loud would be to confront something enormous. That our entire narrative of cosmic history, from origin to present, might be based on an incomplete picture, that we had mistaken our map for the territory. To the public, it still looked like science as usual. Research continued, papers published, missions launched. But behind the scenes, the scaffolding of belief was shifting. It's easy to imagine science as a fearless pursuit of truth, but it's also a human institution full of careers, reputations, funding cycles, academic hierarchies. Revolutions are risky, and cosmology is a particularly slow-turning wheel. So, when a telescope starts unraveling the known universe, the first reaction is not revolt, it's revision. Dr. Elodie Navarro, a cosmologist at the University of Paris, described it best: "We're redrawing the borders of a map while pretending the map is still intact." Her recent keynote focused not on the anomalies themselves, but on how science responds to contradiction. She argued that what JWST triggered wasn't just a cosmological crisis, it was a psychological one, a reckoning with the limits of institutional certainty, because when textbooks become outdated overnight, what do we really know? One graduate student from MIT wrote an anonymous blog post that went viral in academic circles. It read, "They taught us the universe was simple, that redshift told us time, that galaxies formed in order, but now the data doesn't care about the story, it just shines, and we're left blinking in the glare." It was shared, quoted, whispered, not because it was radical, but because it felt true. The silent revision wasn't just happening in equations, it was happening in hearts and minds. Viewers, pause here and ask yourself, what happens when authority hesitates, when certainty falters? Do we double down, or do we dare to step into the unknown? Because science doesn't just describe the world, it tells us how to think about it, and now it's thinking again. Institutions like NASA and ESA haven't abandoned the lambda-c model, not officially, but their latest white papers now refer to it as a framework under refinement. Funding has begun to shift toward alternative models, early dark energy, modified gravity, quantum cosmologies. The silence is not passive, it's strategic. This is how paradigms end, not in explosions, but in edits, and so the cosmos waits not for an answer, but for us to admit we don't have one, because real revolutions don't begin with shouting. They begin when the smartest people in the room go quiet. When we look at the stars, what do we really see? A map of truth, or a mirror of ourselves? As the James Webb Space Telescope continues to flood the scientific community with impossibly early galaxies, warped timelines, and silent contradictions, a deeper question begins to rise, not about the universe, but about us. What if the cosmos isn't broken? What if we're just projecting onto it? In psychology, a Rorschach test reveals the contents of the mind, not by showing images, but by asking the observer what they see: ink blots, symmetrical stains, patterns without meaning, until we assign them one. Cosmology, it turns out, may not be so different. Our models, our theories, even our instruments, all are designed by human minds prone to pattern seeking, minds that crave symmetry, causality, order, minds that feel uncomfortable with chaos, and yet the universe has no obligation to conform to our expectations. In a dimly lit office at the Max Planck Institute for Astrophysics, Dr. Henrik Vollmann scribbled equations on a whiteboard already stained with the dust of old theories. He was revisiting something few dared to admit publicly. Maybe the JWST data isn't the problem. Maybe our interpretation of it is. He pointed to a printout of galaxy JADES G SC120, one of the so-called forbidden galaxies. We see age here, he said to a colleague, because we expect evolution. But what if we've misunderstood what age even looks like? Vollmann wasn't denying the data. He was questioning the lens. Every model we build is layered with assumption that redshift correlates with distance, that galaxies form hierarchically, that time flows forward, and gravity behaves universally. But each of these is a choice, a framing, a story we tell to make the chaos legible, the danger, that we begin mistaking the story for the truth. It's happened before. We once thought the Earth was the center of the cosmos because it felt right. We thought light moved through ether, that atoms were indivisible, that Newton's laws ruled everything, until Einstein pulled back the veil. Each time, we weren't just wrong. We were convinced we were right. How many of today's models will be tomorrow's discarded myths? The question grows louder with each JWST discovery, because, as the telescope shows us ancient, luminous galaxies that shouldn't be there, we respond, not with surrender, but with new layers of theory. We patch, we reinterpret, we bend our models, and that bending says something not just about the cosmos, but about human nature. Dr. Talia Nguyen, a physicist and philosopher at UC Berkeley, sees it as a reckoning. In her widely shared essay, The Mirror of the Stars, she writes, "We are not passive observers of the universe. We are participants in its interpretation. We look up and see structure, but do we see it, or do we impose it? This is the essence of the cosmic Rorschach. When we peer into deep space, what we're really doing is constructing meaning from light. Infrared signals become galaxies. Redshift becomes time. Curvature becomes fate. But every interpretation is a choice. And what happens when different observers make different choices? Some scientists now argue for radically divergent cosmologies. Biometric gravity, emergent spacetime, simulated universes, each of them plausible, each supported by select pieces of data, each a different inkblot. So which one is true? Which theory reflects the universe? And which reflects us? In one lab, a scientist sees rapid early star formation. In another, she sees a fluctuation in lensing. In yet another, a theorist sees proof of a multiverse, the same sky, the same photons, different minds, different maps. Viewers, what do you see when you look into the stars? Do you see randomness or purpose? Do you see an accident or a message? There's no right answer. That's the point, because the cosmos doesn't speak in words. It speaks in patterns, and those patterns are always filtered through bias, through hope, through fear. Just as a child sees monsters in shadows, the scientist sees symmetry in noise. And just as the inkblot reveals the patient's mind, the universe may be revealing our own. This doesn't mean truth is unreachable, but it means humility is essential, because perhaps the most dangerous moment in science is the moment we believe we figured it all out. And perhaps JWST's greatest gift isn't the galaxies it reveals, but the questions it forces us to ask, not just about the stars, but about the eyes with which we see them. Somewhere, beyond the veil of galaxies and redshift, beyond equations and models, lies a truth we haven't touched, not because it's hidden, but because it keeps changing form. Every answer we've uncovered about the universe has only ever unlocked more questions. And now, at the edge of everything James Webb can see, we find ourselves not closer to certainty, but standing at the gateway of something stranger. Welcome to the realm of infinite questions. Because when galaxies appear older than time, when expansion falters and redshift distorts, the problem isn't just with the data, it's with our framework. And perhaps that's where the real mystery lies, not in what the universe is, but in what it could be. What is the universe, really? A vast, ever-expanding sea of matter and energy. A simulation programmed by intelligence beyond comprehension. Multiverse bubble, one of countless others. A quantum hologram. Each idea sounds radical, and yet each one is now considered plausible by at least some faction of the modern theoretical physics community. The first and most enduring idea is that of the inflationary multiverse, a proposal suggesting that our universe is just one bubble in a cosmic foam of endless universes. Some inflate and collapse, others never birth stars. Some follow different laws of physics altogether. In this view, the strange galaxies we see could be cosmic bleed-through interactions. However subtle, with neighboring universes, it sounds unbelievable, but the math, in certain versions of inflation theory, doesn't rule it out. Then there's the simulation hypothesis, popularized by thinkers like Nick Bostrom, and now studied seriously by philosophers and physicists alike. It posits that advanced civilizations, somewhere, someday, might simulate universes for research, for curiosity, or for something else. Could JWST's anomalies, these forbidden galaxies, these warped timelines, be signs of the simulation showing its seams? Some researchers at Oxford have proposed looking for glitches, unexplained patterns, repeating structures, or digital-like noise hidden in the cosmic microwave background. They haven't found any definitive proof, but they haven't stopped looking either. Another frontier, stranger still, comes from the study of emergent spacetime. According to this idea, space and time are not fundamental. They emerge from something deeper: quantum entanglement, information theory, or even consciousness itself. Theoretical physicist Eric Verland suggests gravity may be a byproduct of entropy. Others propose spacetime is woven from quantum bits, like pixels in a cosmic screen. And if space and time are emergent, then redshift, expansion, age, all the scaffolding we use to understand the cosmos could be illusions. Convenient, useful, but not absolute. JWST, by peering further than ever before, might not be looking back in time, it might be looking beneath it. Then there's the wildest idea of all, that the universe is conscious, not metaphorically, but literally, an evolving informational structure capable of self-awareness. Theoretical frameworks, like integrated information theory, hint that consciousness may not be an emergent property of brains alone, but of any sufficiently complex, interconnected system. Could the universe be aware of itself? Could we, in observing it, be participating in its process of awakening? Such thoughts teeter on the edge of science and metaphysics. But when every conventional model begins to strain, the borders blur. And maybe that's the point, because what JWST has done, more than breaking timelines, more than challenging dark matter, is remind us that we still don't know what the universe is. Not really, we know what it does. We see its behaviors, its structure, its glow, but its essence, that remains elusive. Viewers, think about this. We've sent machines 1 million miles from Earth, crafted lenses that bend infrared light, processed the echoes of ancient starlight through and the result, more questions than answers. The Greek philosopher Anaximander once proposed that the origin of all things was the apeiron, the infinite, the undefined. Thousands of years later, JWST may have circled us right back to that same word, because if we are honest, the deeper we look, the stranger the cosmos becomes. And perhaps it's always been this way. Maybe the universe isn't a riddle to solve, but a symphony to listen to, not a puzzle, but a poem. And every telescope, every formula, every theory is a verse added to our growing understanding. Not of how the universe ends, but of how it begins again, over and over. Each time we think we've reached the edge, the cosmos expands further, not just in size, but in possibility. So here, in the penultimate chapter, we stand not on an answer, but on a threshold of infinite questions, of infinite stories, and maybe, just maybe, of an entirely new kind of knowing. In the beginning, there was light. That's how the story goes. A single flash, a cosmic birth, and the long, unfolding journey of time. Galaxies spinning outward, stars kindling into brilliance, planets coalescing, life awakening. But what if that wasn't the beginning? What if what we're seeing now is a beginning again? Because as the James Webb Space Telescope peers further into the abyss, it reveals not chaos, but coherence, not randomness, but structure. Galaxies too, old for the timeline, stars that shouldn't have formed yet, patterns that repeat like memories in stone. These are not flukes. They are fingerprints, and they may belong to something ancient or something recurring. Physicist Dr. Amrita Sen, working with a joint team at CERN and the Indian Institute of Astrophysics, has begun to whisper the unthinkable in her latest papers. That JWST may have captured evidence not of a young universe, but of a cyclic one. Not just philosophically, physically, a cosmos that resets, a reality that breathes. Her team analyzed light signatures from multiple forbidden galaxies and found something odd, a uniformity in heavy element ratios that shouldn't exist across separate regions of early space. It's as if different galaxies, separated by billions of light years, inherited the same chemical fingerprints from something before. Sen's conclusion: we may be looking at the leftover architecture of a previous universe, and if she's right, this isn't the first Genesis, it's the second, or the 10th, or the 1000th. Welcome to the idea of conformal cyclic cosmology, not as theory, but as possible observation. A universe that expands, smooths out, and eventually becomes so diffuse that time loses meaning, only for a new Big Bang to ignite from the calm. No singularity, no end, just renewal. In this model, matter as we know it evaporates. Black holes fade via Hawking radiation, and in the distant future, when all that remains is light, a new universe emerges from pure geometry, from the ashes of what was. The shocking part: JWST might be seeing its echoes already. Dr. Sen isn't alone. Her team is cross-collaborating with researchers, analyzing faint circular anomalies in the cosmic microwave background, what some believe are imprints from black holes in a prior universe. Most of these claims were once relegated to the speculative fringe, but now they're returning with data, because the galaxies JWST sees are not just old, they're too familiar. Their structures, their alignments, their maturity. It suggests not just time, but memory, a kind of cosmic déjà vu. If our universe is not a singular event, but one act in a play that repeats forever, then what JWST has done is not just expand our vision, it's cracked the illusion of finality, and what we see through the crack is stunning. Imagine this. Each universe passes something to the next. Not matter, not energy, but information, encoded into the very structure of space-time, like DNA passed through generations. And what if, just what if, life is part of that continuity? The idea isn't new. Russian cosmists, ancient Hindu texts, and speculative physicists alike have long imagined reality as cyclical, but never before have we had data that pointed so provocatively toward it. It forces us to ask, is the universe evolving not just outward, but forward, not just into more stars and galaxies, but into greater complexity, into consciousness? Because if time is reborn and stars reignite and atoms reassemble, what prevents life from returning? What prevents us? Dr. Sen calls it informational cosmogenesis, the idea that every cycle seeds the next, not only with physical conditions, but with the capacity for awareness, for inquiry, for questions. So perhaps we are not the first to ask where we came from. Perhaps we are only the latest, and what JWST captures in its golden mirrors may be the last light of those who asked before us. A second Genesis is not just the rebirth of matter, it's the rebirth of curiosity, and in this light the telescope becomes more than an instrument. It becomes a bridge from what was to what is, to what might be again. So viewers, now pause, take a breath, look up, because that galaxy you're seeing at the edge of time, it might not be the first of its kind, it might be the first of this kind, and that changes everything. Because if this is a second Genesis, then everything we thought was ending might only be beginning again. The questions are no longer just scientific, they're existential. What happens after the end? Who were we before the beginning? And if the cosmos keeps remembering itself, then what role do we play in that memory. We are not just observers, we are echoes, we are continuity, and as the telescope stares into the cold, ancient dark, we are the warmth staring back. The universe just blinked, and in that flicker, we glimpsed eternity. Maybe we're not at the center of the story, but part of its rhythm. If you believe the cosmos still holds secrets, subscribe and stay curious. Comment your theory below, because one voice, one question, might light the path to our next beginning.